obviously first I want to thank the organizers for the opportunity to give this talk at this very nice conference. And this talk is based on joint work with my supervisor, Stefan Weigert, at the University of York. And it's about a Gleason-type theorem for qubits based on mixtures of projective measurements. So before we can talk about Gleason-type theorems, I need to introduce to you what Gleason's original theorem was, if you haven't heard of it, or remind you of it if you have already heard of it. So the very basic idea of Gleason's theorem is that if you postulate that you can perform projective measurements on quantum systems, then Gleason's theorem tells you that you necessarily can represent states of your quantum system by density operators and calculate the probability of outcomes of your measurements using the Born rule, which is just the trace rule here, where pi is the represents the outcome and rho represents your state. And the reason you want to do this is in order to simplify the postulates that you have to make in order to recover quantum theory, because they are notoriously abstract compared to other physical theories. So how does this magic happen? So we could set up our scenario like this. So we could first postulate this thing H, which is that a quantum system may be associated with a separable Hilbert space. So pretty standard. And then we can postulate projective measurements, which is just to say that measurements can be represented by collections of orthogonal projections on our Hilbert space H, which sum to the identity. And each one of these corresponds to an outcome of our measurement. So then, instead of continuing and postulating how to represent states in this theory, we could then think about what a state should do naturally. So what it should do is that it should specify a probability for the outcome of any measurement that we can perform on our system. And that makes sense because if you have two different preparations of your quantum system, and then any measurement that you could feasibly perform on them, if that gives you the same statistics for these two preparations, you want to consider those as the same state. And similarly, if you get different statistics, you'd want to consider those as different states. So if we write this down mathematically, then our state is just going to be a map F from P of H, which is the lattice of projections onto our Hilbert space H, to some probability. And we also want that these probabilities sum to 1 for any given measurement. So these are going to be the two requirements on our state. And this is like the thing that you need to understand, the main thing you need to understand for the rest of the talk. So basically, states are probability assignments on the objects which represent your outcomes of measurements. Okay, so now we can apply Gleason's theorem, which tells us that if H is a separable Hilbert space with dimension of at least 3, and we'll come back to that a bit later, then one of these functions that we've talked about, so one of these probability assignments on our projections, which gives things which sum to 1 for any collection of projections which constitute a projective measurement, then any map of this form can necessarily be represented like this. So this function of a projector is given by the trace of this projector with some density operator, which is fixed. So in other words, each one of these maps has an associated density operator, right? So then we can represent this map in terms of this density operator. And then the probability is just given by the Born rule, which is what we wanted. So now we get back to this thing, which is slightly upsetting, that this theorem doesn't hold in dimension 2. So it doesn't hold for qubits, which is pretty sad. And it's pretty easy to see why this is true. So for qubits, we can represent these projections on the surface of the Bloch sphere. And then any measurement would just correspond to two antipodal points of this sphere. So then our condition that the probabilities need to sum to 1 just tells you that you need to assign a probability here, and like if you assign probability p here, then you can assign 1 minus p here, and our condition will be satisfied. So then there are a whole bunch of ways that you could do this which don't take the form that we want in terms of a density operator. So we could assign a half everywhere, and then just assign 1 here and 0 here. And there is no density operator that does that, but we've still satisfied our condition for being a state. So yeah, we're done for. But don't get too upset, because generalized measurements come to save the day. So whereas before, so these were our two postulates that we had before, and now if we replace our measurement postulate with a generalized measurement postulate, which is pretty similar, except for now measurements are represented by collections of effects which sum to the identity, where each effect corresponds to an outcome of a measurement. So these are basically POMs or POVMs, and an effect is just a self-adjoint operator between the 0 operator and the identity. Okay, and then we're using our same natural definition of a state as a probability assignment on these objects which represent our outcomes. So this is E of H, the effect space, and we require that these probabilities sum to 1 for any POM. So now we can apply our first Gleason type theorem, which is by Paul Bush in 2003. So now we let H be any separable Hilbert space with dimension greater than or equal to 2. Hooray, we've got qubits back. And we require that these probability assignment, the probabilities sum to 1 for any collection of effects that constitutes a POM. And then his result shows that these maps can necessarily be written in the way that we want. So then our states are necessarily correspond to density operators, and our probability is given by the trace rule again. But then this raises the question of, is this condition too strong? Is it stronger than it needs to be? Because in all other dimensions, we only required this condition to hold for projective measurements, which are like a very small subset of all POMs. So that's what we're going to consider now. So yeah, so we can represent this rectangle. If this rectangle represents the set of all POMs, then, and this circle can be the set of projective measurements, PVM. So this is for the qubit case. Then we could represent the set of all POMs with at most 2 non-zero outcomes by this ellipse, and similarly the set of all POMs with at most 3 non-zero outcomes here. So is there going to be some set in here from which we can also prove a Gleason type theorem? And the answer is yes, obviously. And to describe this set to you, we need to remember what projective simulable measurements are, and we've had these mentioned or explained in a couple of talks before, but I'll just do a small recap with an example. So imagine that you have a black box with a Stern-Gerlach apparatus inside it, and with probability 1/2, it performs a measurement in the Z basis, and otherwise it performs a measurement in some other basis. So then you get that the probability of, and we say if we get this 0 outcome here, then the box outputs 0, and if we get this outcome psi here, then the box also outputs 0. So then the probability of getting 0 is, so there's a half a chance that this measurement is performed times by the probability that we get 0, plus a half a chance that this measurement is performed times by the probability that we get 0. And we can rearrange that into this expression, which is just a trace of some effect with our density operator. And if we do the same thing for the 1 outcome, then we get this effect here. So essentially, we have implemented this POM, which is not a projective measurement. So then if we can implement any POM in this way, then we call that POM projective simulable, because we've simulated it with projective measurements. So then so in the case of qubits, this set would look like this. So obviously it contains all projective measurements, because you can simulate projective measurements with projective measurements. And it was already mentioned that you can always simulate all 2 outcome POMs with it, but you can't simulate all 3 outcome POMs with it, and so on. So just an example, so your 2 outcome POMs will usually look like this, so some effect and the identity minus that. And an example of a 3 outcome POM that is projective simulable would be this thing, so just the half times some effect, a half times that effect, and the identity minus it. So now we can state our main result, which is if you let H be some finite dimensional Hilbert space, and then we consider probability assignments which necessarily sum to 1, but only for projective simulable POMs. So probability assignments that are consistent with the idea of being able to perform projective simulable POMs, then we necessarily get that these maps must take the form that we want them to, so being the trace of the effect with some density operator rho. I'll quickly the proof is super easy, so I'll quickly just describe it to you. It only has these 2 steps, so try and stay with me if you can, but it's not that important. If you remember, we said that these 2 types of measurement are projective simulable. So ones with 2 outcomes, and then these special type of 3 outcome ones. So then if we apply our rule that we need the probabilities to sum to 1 for these types of measurement, then we get that this thing needs to be 1, and also this thing needs to be 1, therefore they're equal to each other. And this simplifies to tell us that we can just always take out a factor of a half from our function. So that was step 1. And step 2, you can do the same thing for these other 2 types of projective simulable measurement to give you this equation here. But then these have all got this half in, right? But we learned that we can take out a factor of a half. So then we just get that our function is necessarily additive. And that basically means we're done, because this is equivalent to the condition that we had from Paul Bush's result, that the probabilities need to sum to 1 for any POM. So what we've essentially shown is that if your probability assignment is consistent with projective simulable POMs, it's necessarily consistent with all POMs, and therefore we can use the existing Gleason type theorem that we looked at. So then how can we apply this result? So we could take our first 2 postulates that we did for the original Gleason's theorem, so that quantum systems are associated with a Hilbert space, and to postulate that projective measurements exist. And then we can add in this 3rd postulate, that if we perform a classical mixture of some projective measurements, so like pi1, pi2, so on, and pi1 prime, pi2 prime, with probabilities p and 1 minus p, then we postulate that this is represented by this POM here, where you just mix each term. So for example, if this is a cross-section of the Bloch sphere, then these 2 points connected by this straight line represent a projective measurement, as do these 2. And if we say that this represents the 0 outcome, and so does this of these measurements, then this postulate would tell us if we mix the 2 measurements with equal probability, then the 0 outcome is given by this point that's halfway in between them. And we can see how this might give us more power, because if we also mix these 2 measurements, then an outcome of this mixture will also be represented by this effect. So we used to have this problem in dimension 2 that our projectors only featured in 1 equation each, but now these projectors are going to be related to each other where they weren't before, and this helps us out. So our result shows that if you postulate these 3 things, then you necessarily get that states have to be represented by density matrices. So then we can go on to ask, could there be an even smaller set of POMs from which we can prove a Gleason type theorem? And the answer to this is also yes. So if you remember in the sketch of our proof, what were the measurements that we needed? Well, we needed 2 outcome POVMs, 3 outcome ones which had this special form. These ones here, which if you look at them, actually only have 2 outcomes, so we've already counted those. And then finally, these other special 3 outcome ones. So then if we define some set PSM prime, which only consists of POMs of these 3 special types, so the 2 outcome ones and these 2 types of 3 outcome ones, and this would sit here, then our proof actually shows that this set is also sufficient to prove a Gleason type theorem. And then could there exist an even smaller set of measurements? Don't know yet. The answer is maybe. Hopefully we'll figure this out soon. So that brings me to the end. So the main thing we have shown is that if you postulate projective simulable POMs, then in the same way that Gleason's theorem tells you that you get density operators in the Born rule, our theorem tells you that you can also get that, but our theorem also applies in dimension 2, whereas Gleason's theorem doesn't. And we've identified a postulate that you can add to the original setting where Gleason's theorem applies in order to extend the result to dimension 2. And thirdly, we identified an even smaller set, which we called PSM prime, from which you can prove a Gleason type theorem. And this represents a significant weakening of the results that exist so far, which are that you require your consistency equation to hold for all POMs, or there's also a result that if you require it to hold for all 3 outcome POMs, that's sufficient. But then if you remember, our new set is a strict subset of both of those. So then the result is stronger. And for future work, as I mentioned, it would be nice to figure out whether this set PSM prime is minimal, in the sense that can you take any POMs out of it whilst still being able to prove a Gleason type theorem from it. And secondly, it would also be good to generalize our result to infinite dimensions, because Gleason's original theorem and Paul Bush's extension of it hold in infinite dimensions. However, projective simulable measurements haven't quite been thought about in infinite dimensions yet. But if we could do that, then we might get this result to hold for all dimensions. So that is the end. Thank you for listening, and here's the archive reference.
Thank you very much.
It was a nice talk, thank you. There is a result from some time ago from Carl Caves and Chris Fuchs and others that there's a similar Gleason type derivation. Obviously you are aware of it. How does it relate to your work?
Yeah, so they just show this again in with a different proof. But I think theirs actually only holds in finite dimensions, but they have a slightly different proof. And then there's a bit more in the paper where they put an extra requirement on this f necessarily being continuous, and then you can throw away loads of these conditions and still get your function to have this form, because the continuity is really strong.
So thanks for the talk. Do we have some interpretation for PSM prime, except saying is this?
No.
Okay.
Yeah, that would be nice. So that kind of falls into this question of whether there is a subset of PSM prime that would be sufficient, because maybe that would have a nice physical motivation like the projective simulable one does, but PSM prime doesn't really, unfortunately.
Okay, thanks.
So you're concerned with minimality of PSM prime, but you could be also concerned with uniqueness. Some other set.
Yeah, so there could be some set which doesn't necessarily overlap with it. Yeah, that is also a possibility. I think it would be good to make sure that your set includes POMs which have all effects included in them at some point, right? So PSM and PSM prime does, because they contain all 2 outcome POMs, so then you can stick any effect and I minus it, because you want your map to act on the full effect space. But yeah, I would also be open to sets which overlap but are maybe smaller in some sense as well.
Okay, any other further questions? Okay, if not, let's thank Victoria and all the speakers of today.